Jeff Bill. I realized I know Jeff since he was undergraduate student at Berkeley. When he played lead guitar on our several songs, among them Rasta song and stuff. If you haven't heard songs from Exit, contact me, I can play them for you. I think they still exist. Jeff was playing, I believe, bass and lead, right, on Rasta songs. Then he went to MIT for a while. Then he realized his mistake and came back to get his PhD at Berkeley, where he got it in basically doing speech. And just mentioned, I realized that he's been involved in a number of things we were working on, very often indirectly, just like bumping to somebody at the coffee corner and making suggestions which revolutionized the field. But anyways, he said that I should say only bad things about him, so far I said good things. So bad thing is, I think he still plays guitar, right? I believe he was in a number of San Francisco bands. I don't know how it is now, but now he is a professor of electrical engineering or computer science at the University of Washington, and he's of course well known as a machine learning person, and I hope that still a little bit a speech person. So I'm very happy to have him here, and Jeff, the floor is yours.
Thank you very much, Enoch, for not saying too many of the bad things. And we're going to talk about submodularity in big data. And it's very funny because it's very dangerous these days to give a talk that has big data in the title, because everybody has a talk that has big data in the title, and so when you hear the word big data, you see it in the title, and you say, oh my god, not another one of those big data talks. So hopefully by acknowledging that you should never have big data in the title, it will be okay to have big data in your title. So, and in fact, we will then talk about what at least we think of as big data and sort of look at a tripartite description of big data in terms of the three technical terms I like to call it: good, the bad, and the ugly. And in particular, how that understanding, at least from that viewpoint of what big data might provide us, that helps us to see why a class of functions that I've been doing a lot of work on recently, and me and my students and colleagues have become extraordinarily interested in, and that's the class of submodular functions. And hopefully I'll at least have some success in convincing some of you that these are interesting mathematical objects to look at. And then we'll apply them to three fairly, what might seem distinct settings, one of which is document summarization, which is actually work that is now about a year old, but then talk about some more recent stuff on maybe what could be called speech summarization, and also data subset selection for statistical machine translation, which I think some people here are working on MT or SMT. Can you raise your hand? Doing SMT, one person, Sanjeev. Sanjeev is the SMT representative here at JHU. What's going on? Okay, one other person. All right. So maybe I should very quickly go through that section, and then conclude with a little bit of work on general summarization. So okay, so here's the fun part of it. Raise your hand if you have never seen this slide before. Oh, okay, this is a lot of people have not. So this is basically a typical slide that you see when people start talking about big data, and what it does is it shows the enormous and incredible growth of big data over the years. And as you can see, the amount of data, and in particular the amount of unstructured data, which is the green bar, is growing enormously. Now, by unstructured, we mean things like images or speech utterances or text strings or graphs or radar signals or other sorts of data which isn't really compartmentalizable into sort of things like tuples and records, things that typically people find in sort of the traditional database. And there are lots of quotes that you see, for example, like every day we create 2.5 quintillion bytes of data. and 90% of the world's data has been created in the last 2 years. Those sorts of things are basically meant to inspire awe in all of you. I hope everybody now is awe-inspired by these quotes, because that's what their intent is. The good, the bad, and the ugly. So let's talk about this. So I think that there are sort of 3 sides of big data. The good is something that I think is not really mentioned that much in the context of big data. And this actually goes back to a paper from the early 70s by P.W. Anderson entitled Moore's Difference, or Bigger's Difference. And he was a dense matter physicist. And at that time, people were actually looking at statistical models and of real-world objects and real-world phenomena. And the idea was that when you actually when you study an object in the aggregate sense, it's not really correct to use sort of the fundamental laws of sort of constituent parts of that object to study the way it behaves in the aggregate. And there are a number of examples of that you can use. For example, when you're looking at when you're studying, for example, water molecules in a vat, and you have maybe many of them, it's not really correct to study them using the rules of, say, n-body collisions. And instead, it's better to use sort of emergent rules that come about, like, for example, the rules of fluid dynamics. And there are many instances of this. For example, with water molecules, like when you're looking at a small number, then you study them as an n-body problem. And when there's a medium set of molecules, you would use the rules of fluid dynamics. And when there's a large set of water molecules distributed around an Earth-sized body, then you'd use properties of weather systems. And the idea is that one would never gain anything, or in fact it's actually officially, in some sense, incorrect to use these microscopic rules to study the macroscopic properties. And the idea of this paper at the time was that when you look at something at large scale, bigger is not just bigger, bigger is different. Or there's the famous quote by Karl Marx, which is that quantity has a quality all of its own. And this can be applied to not just things like physical models, but can also be applied to neurons. When you look at the behavior of an individual neuron, it behaves very differently than the property that arises when you connect hundreds of billions of neurons together, which are things like consciousness. When you look at pixels, individual dots, there's pointillism, and a whole scene emerges from lots of dots that are sort of situated in a coordinated fashion. And it's no longer sort of correct to sort of think of them as just an RGB pixel, but they're new properties. And there are many instances of this. And so the idea is that maybe big data has similar sorts of properties, that when you have enormous data sets that are starting to become available today, properties of that data that are not really available when you only have a small subset of the data, or when you only have a small set of data, are different than what kinds of things you can do when the data gets very large. And I think this different information that can actually come about from big data is one of the things that people are beginning to be able to exploit, and is one of the reasons for the successes that big data is having in certainly business circles. And it's one of the things that you're sort of reading about when you read about big data in sources like the New York Times. And there are lots of these kinds of quotes that you get these great efficiency improvements by using data-driven decision-making, and these massive improvements, and 417% increase in revenue, and all these sorts of things. And of course, everybody, as a result of seeing these kinds of quotes, are very excited about it. But I guess the new take on this that I think I want to say is sort of putting it in the context of this old article by Anderson, which is that bigger is not just bigger is really different. And there's different things that can be said from big data than that can be said from small data. So that's the good side of big data. Bigger is different. The bad side is that there's a number of bad sides. One is that it leads to what potentially could be called information overload, which was also a concept that was known well back in the early 70s. And that basically is that the amount of input exceeds the decision maker's capacity to actually make an informed decision from that input. There's just too much stuff, and you just can't look at it all because it's just too big. And so therefore, even if there is information to be gleaned from a lot of news articles or something, you just don't have time or you don't have the capability, or the compute power, if you happen to be a computer, to actually process that. And so this basically is now maybe not so much a bad, but this is a challenge. And there are computational challenges. Actually, I seem to be missing the bottom part of the slide. But basically, there are new computational strategies in database systems and computing systems and parallel computing, all of which actually are not completely solved, but basically are research challenges, which basically involve figuring out ways that one can compute efficiently with these large data sources. So another thing that might be seen as bad about big data is that there are, of course, lots of descriptions of big data. This is just sort of a brief scan on Amazon, looking at what books have been written about big data. Big data analytics, or taming the big data tidal wave, or the human face of big data, or big data government. There's lots of these titles, and all of these things, of course, are designed to sort of attract you to become interested in the idea of big data. My favorite example is Big Data for Dummies. If anyone reads any book about big data, one should read this one. Famous one. And at some point, when one of these for dummies books has been written, then you sort of start thinking, maybe there's a little bit of hype going on. And indeed, there are many, many articles now, and one of the reasons why people don't like the word big data is because people say it's getting overhyped and it's the buzzword and everyone's using it, and you can't read a newspaper article without reading about how great big data is. There are articles by Marcus, steamrolled by big data. What will you do next? David Brooks' article, who's saying that basically big data is sort of meant to sort of remove humans from the loop and do everything that humans can do. What big data will never explain, so on and so forth. So it's a buzzword. This is probably a quote that some of you have seen before. Big data is like teenage sex. Has anyone seen this quote? Everyone talks about it. Nobody really knows how to do it. Everybody thinks everyone else is doing it, so everyone thinks they're doing it. In some sense, big data is a buzzword. But on the other hand, there's something real. And I really like this. There's a rebuttal article by Andrew McCarthy at Harvard Business Review, which is basically saying that people who are working on big data are not saying things that people who are saying people working about big data are saying. So in other words, we're not saying a lot of these things that they're saying we're saying about big data. We're saying much more mundane things, which is that you can do different things by big data, but we're not saying that big data is going to answer, it's going to be all end all of decision science. So here's now the ugly side of big data, and the ugly side of big data is really what we're going to be talking about in this talk, and that's the issue of redundancy. So usually it's the case when data is collected somewhat indiscriminately and without very much coordination. So when you add a piece of data to a data pile, you're not being very, very careful, primarily because it's not really cost efficient to do so. You're not being very careful to ensure that those additional samples are saying anything different than what you already have. And so big data really leads to big redundancy. So as a result, then you have this problem of information overload. Now, I think that maybe information overload is probably not the right term if there's big redundancy. And maybe instead the right term should be sample overload, because it's not that there's necessarily more or too much information in this large chunk of data. Maybe there are instead too many samples to process. So that means, for example, that you have too many documents, too many web pages, too many photos, too many Facebook friends, too many parties to go to. I mean, there are too many samples in the data to represent the actual information that's contained within the data. Now, of course, what do we mean by information? And that's where we start getting into the next phase of the talk. Now, we're all, in some sense, machine learning scientists, whether we're working on speech or language, whatever else we're working on here. And as data sets get bigger, and as we have big training data sets, this is great. I mean, as you all know, Fred Jelinek, I think he was the first one who said there's no data like more data. Right? So big data is great. There's a problem, however, which is that we have a diminishing returns kind of property. So this is a very typical curve that you see. This particular one comes from speech recognition, where the horizontal axis is the amount of training data used, and the vertical axis is the performance. And basically, you can see that you start getting diminishing returns. If you keep doubling your data, the amount of expense, computational and sort of other resources you need to spend on actually training a system doubles, but the performance doesn't double. The performance saturates eventually. And this is also true in machine translation. And doing a quick search actually shows that this kind of problem occurs often. You have this diminishing returns property. And the basic idea of diminishing returns is that the more you have, the less valuable is anything that you don't have. So if you have one Facebook friend, that Facebook friend is very valuable to you. But if you have 10,000 Facebook friends, getting one more Facebook friend is probably not so important. Okay, so here's big data. The good, which is big data, is different. There are emergent properties. The bad is that it is big and there are lots of new computational challenges to deal with, and also maybe it's being a bit overhyped. And maybe the ugly, which is big data, is overabundant. And so what we're going to really address in this talk is this third point, the overabundancy of big data. So basically, what we want to try to do is answer the question, and that's answer the following question. Can you make statistical decisions cost effectively using small data sets? Now, by cost effectively, what we mean is that you can get high enough accuracy at low enough cost to make it worthwhile. And by low enough cost, I mean that, for example, the data set, if you had a very, very small data set, then it's not very costly to train a model on it and maybe to use it and to store it and to do stuff with it and to analyze it. Small data is easier to work with, so it decreases the cost. Now, usually the problem with small data is that it leads to a loss in accuracy. So the goal then is to somehow extract core data from big data. Now, what properties might core data have? Well, on the one hand, it should ideally retain as much of the information as is in the big data. And if there are, in fact, for example, emergent properties in the big data, then those properties should somehow still be contained in the small data. Point number two is not a compression. Because compression, of course, whether it's lossy or lossless, does reduce essentially the number of bits necessary to actually represent the data. But what we're interested in is not so much compression, because we don't want to change the code book. We want basically any parser or any system, any encoder, any decoder, anything that can actually work on the big data should also work on the small data. We don't want to change the form of the data into something that only a decompression algorithm can work with. Which, by the way, whether you're doing lossy or lossless compression, also stores the size of the original data, and also to use it needs to restore the original size of the data, which is not what we want. So we, in some sense, want sort of a subset selection process. And we don't have the desire that we need to construct the original size. Like we're not trying to decompress. We're not essentially saying we want to go from the core data back to the big data. We want, in some sense, the core data to act as a surrogate for the big data. So it's really distinct from either a lossy or lossless compression. So it's really more like a summarization process, or like a cliff noting process, which is what we mean by core data extraction. So this is where we get to the data subset selection problem.
Should we be making a connection with a stratified set?
That we're going to talk a little bit about sampling. We'll see some results on that. So I'm going to get to that. So here's sort of the idea. So we have a big data set, and let's sort of use V to sort of represent our big data set. And let's say it's of size n. It's a finite data set. And maybe we can select some subset A to be useful as a surrogate. And the ultimate goal is that any question we might be able to ask about B using enough computational resources should ideally and hopefully be able to be answered in a reasonable, having reasonable accuracy using only A. And ideally A should be pretty small. And so one example of this is extractive document summarization, which I'll be talking about. Another example of this is speech, automatic speech recognition, data subset selection, which I'll also be talking about. A third example, which is listed here for some reason, is machine translation, data subset selection for a particular training, for a particular test set. But before we do this, let's introduce submodularity. So can I just have people raise your hands if you've heard of submodular functions before? So not too many people. Raise your hand if you really know about submodular functions. So if you're okay, so good. So I think that this will be a reasonable introduction. So here's basically a little bit of introduction about submodular functions. So we're given some quality function, f. Okay, so f is a function that maps from 2 to the v to the real numbers. And 2 to the v is basically a representation of all subsets of a given set v. Okay. So any given subset is contained within 2 to the v. And then if we are given a particular subset A, then f of A in some sense measures the quality or the value or the cost or something associated with that subset A. Now, maybe f of A, let's say it just measures the quality. We might also have, say, essentially a cost associated with that subset. Like the cost might be its size. We want to have small size subsets. Or we might have an individual cost associated with every data item contained within capital D. And let's assume for the moment that the cost function is just a simple additive function that basically says the cost of the set A is equal to the sum of the costs of the individual items contained within A. And so that includes, for example, like the size, the cardinality function, which is the cost function. And by the way, if there's any questions, please ask me. So there are two sort of optimization strategies that might be seen as a method for extracting a representative subset using f as a quality measure. So basically, in some sense, what we want to do is extract a subset of data that has a similar quality. And there's two ways of doing this. The first way is really to say, we've got a given budget, B, and we're only interested in subsets whose cost does not exceed our budget. But amongst all of those subsets, choose the one that has the highest quality. So that's this method, which is the best within a given budget method. A second method is sort of where sort of quality is of prime importance and budget is of secondary importance, which might have, you want to essentially have a quality assurance. And the quality assurance is maybe alpha. So you're not interested in any subset whose quality is less than alpha, but amongst all subsets whose quality is greater than or equal to alpha, you want to choose the least costly. Which might mean you choose a very costly subset, but quality is of prime importance, so that's fine. It doesn't matter. So the two very different optimization strategies, they're both very similar in a certain sense. They're both, in general, hopelessly intractable. Not only are they NP complete to solve, but they're information theoretically complex. They're exponential, in general, to find any sort of solution that has any guarantee of quality or accuracy or budget. So what do? Well, you can write a heuristic. Or instead, what one can do is make assumptions about the function f. And it turns out that if f is monotone submodular, non-decreasing monotone submodular, then it turns out that those two functions can be computed approximately, can be computed with certain quality assurances associated with the solution. And in fact, it turns out that very, very simple algorithms can actually compute answers to those problems very efficiently. And the answers are very, very high quality. And it turns out that the simple greedy algorithm actually does this. So the general problem is NP hard, and it's actually worse in many cases. For submodular, let's say, so going back to these two problems, let's now assume that f is submodular. Now, before I even define submodular, I want to tell you what algorithms actually end up having, what algorithms do it. So this is an old result that comes from the operations research literature, and actually these folks back in the 60s and 70s were actually working on problems like bin packing. How do you pack as many boxes into a truck as possible? And it turns out that turns out to be a form of submodular optimization. And the Nemhauser 98 showed that if you actually have a monotone non-decreasing submodular function that's also normalized, the simple greedy algorithm, which basically sort of chooses next whatever looks best, which is equation 3, that algorithm gives you a 1 minus 1 over your approximation. So what that basically means is that the solution you get at any stage I, where I is a particular size, ends up being no worse than 1 minus 1 over e, which is approximately 0.63, no worse than 1 minus 1 over e times the best you could possibly choose. And the best you could possibly choose, of course, is this exponential problem, or this NP complete problem here. And it turns out, moreover, that there's a result by Conforti in 84 that shows that depending on the curvature of the function, the curvature is sort of something analogous to curvature in a continuous function, and I don't want to get into the actual definition, but if you're really interested, you can ask me and I'll tell you the definition of curvature. But basically, depending on the curvature of the submodular function, the bound is actually usually much better than that. And in practice, many of the functions are not so horrendously curved, and so the approximation guarantee sometimes is in the mid to high 90s even. And this was shown to be non-improvable in polynomial real time. So meaning unless p is equal to np, you can't do any better than these approximation guarantees in any polynomial term algorithm. So basically it means that the greedy algorithm is the best you can do, even though the greedy algorithm is so fast. And moreover, there's an accelerated variant of the algorithm that basically speeds of the algorithm, roughly n log n. Sometimes it's linear even. It's very, very fast. It's incredible, the accelerated greedy algorithm. So you can actually do these kinds of problems, find good quality subsets within a given budget in very, very low order polynomial time, which basically means that you can scale this to big data problems.
So Jeff, in this complexity analysis, the unit operation is an evaluation effect?
Yeah, this is under the Oracle query model. It basically means that you can query the function that many number of times. So this is interesting because something about submodular functions, as I was saying, is that there's an exponential number of degrees of freedom in instantiating a submodular function, and you're only querying them a very small number of times and still getting these guarantees. So, yeah.
No, but the reason I asked is because depending on your problem, and I think one of your problems is going to be selecting data for something, right, for discrete recognition translation. Evaluating F may be non-trivial, right, in this incremental way, because it might involve multiple.
That's right. That's exactly right. And so the question was, when, so these are complexity theoretic results in terms of the Oracle query model, which basically says that if querying a particular F is exponential, then obviously that's not going to do you any good. So in general, you have to worry about these sorts of things. And you actually, usually, so for many of the submodular functions, in fact, some of the ones I won't talk about, I will adjust this very problem, and it will be one of the reasons why this particular function is useful will be for this very reason. And we also have some other theoretical results which are in the pipeline which help with this exact situation. So I can talk to you about that either during the question and answer session or offline. Yeah.
So I just wanted to clarify something. I assume that the Feigen 1998 result means this can't be improved for general submodular functions. If you have a specific submodular function, you might wish to do much better, right?
Actually, this result was for the set cover function, which is a very simple submodular function. And submodular functions are much more general than set cover.
But for knapsack, for example, you can obviously do better, unless you're going to stand on the difference between polynomial and pseudo-polynomial.
Yeah, there may be certain submodular functions for which you can do better, but in general, cover is already, set cover is already a pretty darn simple function, and the kinds of submodular functions that we want to use are already immediately generalizations of set cover. So this is sort of the best of cases when you're only using set cover is the worst case result.
Excellent. And this doesn't hinge on the difference between polynomial and pseudo-polynomial?
No. Okay, so what is a submodular function? So there's two equivalent, actually there's quite a few different equivalent definitions. I'll give you two of them. The first one basically says that a function is a submodular for all subsets A and B. F of A plus F of B is greater than equal to F of the union plus F of the intersection. And that's a definition that I have a slide in a minute that I hope will give you some intuition as to why that's the case. A definition that is slightly more attractive, intuitive, I don't know, for some people, is the notion of diminishing returns, which basically says that if you have two subsets, A and B, A is a subset of B, and you have some other item V, which is not in B, then basically it's saying that the incremental gain you get when you add V to A, because A is the smaller set, is going to be greater than the incremental gain you get when you add V to B. Okay, so basically, this is exactly the example of Facebook I gave you before. If V is a friend, the value of V as a friend is greater in the context of a smaller set of friends, A, than it is in the context of a larger set of friends, B. Another thing I want to mention is, of course, just the notion of modular function. So if this thing is always equal, if that inequality is always equal, then the function is called a modular function. Now, if a function is also normalized, so basically normalized function means that f of the empty set is equal to 0, and monotone non-decreasing, which basically means that supersets always, or supersets can never decrease the valuation, then this is called a polynomial, a polymatroid function. So normalized monotone non-decreasing submodular function is called a polymatroid function. So one example which is near and dear to many people's hearts is consumer costs. And one of the most ubiquitous costs to consumers is McDonald's. So it turns out McDonald's is submodular. So the cost, in this particular case, F represents a cost. So F is the cost of a Coke and fries plus the cost of a fries and a cheeseburger is greater than the cost of a Happy Meal plus the cost of fries. Now, why is this the case? Well, just doing this is the first definition of submodular. All we need to do is just rearrange the terms, and we can say that the incremental cost of Coke in the context of fries is greater than the incremental cost of Coke in the context of fries and a hamburger. Why? Because of the Happy Meal deal, where it says if you buy a fries and Coke, if you buy fries and a hamburger, then they'll throw in the 64-ounce Coke for free. Right? So McDonald's is therefore submodular. Maybe a slightly more mathematical definition is in the context of matrix rank. So the matrix rank function basically is the following. It basically says you've got a matrix, and this is a particular example of a 4x8 matrix. And you have an index set, V, which corresponds to the columns of the matrix. And for any given subset of column indices, the rank is basically the rank of the submatrix corresponding to that set of columns. So for example, if you set A to be this, then this is the first three columns, this is the second three columns, C would be these columns. Here are a couple of other sets which I'm going to skip over. So the rank of A is 3, because it spans the dimension. The span of the dimensionality of the space spanned by those three vectors is 3. The dimensionality of this space spanned by the vectors indexed by the set B is also 3. The dimensionality of the space spanned by the vectors indexed by C is 2. That's actually a mouthful to say. It took me several years to learn how to say that. So if we take A union C, since C is in the span of the space spanned by the vectors indexed by the set A, then therefore when you add C to A, it doesn't increase the rank, since the two vectors in C are linearly dependent on the vectors A. Similarly, C is dependent on B. AR is dependent on A, and BR is dependent on B. But BR is not dependent on A, and so basically BR spans a new dimension, so that therefore increases the rank. And AR also increases the rank. Then if you take the union of A and B, that also has rank 4. In fact, that's the maximum rank of that matrix. And then if we take the intersection, that has rank 1. Now here's the key thing. So the rank of the intersection is 1. The rank of this other two-dimensional subspace is 2. But that two-dimensional subspace corresponded to dimensions that were spanned both by A and by C. Both by A and by B. I mean, remember, because we have this property. This property is there. And so therefore this means that the rank of A plus the rank of B is greater than the rank of the rank of the intersection. So therefore the rank function is submodular. And so there's a nice way of describing this graphically, which basically says that when you look at the rank of A and the rank of B, in some sense you're taking twice the rank of the common span. So the common span, it turns out, are these vectors C. So the idea is that you're counting this stuff in blue twice. When you take the rank of the union, you're taking the common span only once. And when you're taking the rank of the intersection, you're only taking the rank of the common index. And because the rank of the common index is never going to be greater than the rank of the common span, you have the common index corresponding to this purple region is a subset of the blue intersecting region. And so therefore it can never be greater, and so therefore you have submodularity in the rank function. So I guess the key phrase to remember here is that the rank of the common index is no greater than the rank of the common span, and therefore rank is submodular. Now, here's a potential way of using rank of dealing with the big data subset selection problem. So let's say that every data item is represented as a big giant vector in some vector space. And we have the number of columns in this matrix corresponds to the number of data items. And what we want to do is find a subset A of column vectors that has full rank. Okay, so any other vector that's not chosen A will be linearly dependent on the vectors that we've chosen, and so therefore won't provide any additional information, at least as measured by this matrix rank function. Right? Now, there's a number of problems with this, on one hand, in which I hope you are imagining. One problem is that, well, wait a second, this is just a linear space in matrix rank, and what if it's not possible to actually represent data items in this space, and how high a dimensionality of the space does it need to be, and how do we actually construct this particular space? And moreover, here's the sort of most insidious problem, which I imagine Sanjeev is probably going to ask me about if I don't answer right away. Is the following. So basically the rank is sort of an all or nothing information measure. So in some sense you can think of rank as an information measure. Right? The dimensionality of the space spanned by a set of column vectors in some sense represents the information contained within that set of column vectors. At least that's how we're using it. But the problem is that when we add a new vector, it's an all or nothing thing. Either we span a new dimension or we don't. It's a unit increment property. You know, there's no notion of partial information. It's not like I can say, well, this new guy sort of adds a little bit of new stuff, but there's some amount of redundancy with respect to what we already have. And because of this unit increment property of matrix rank, it may not be natural. So what function do we all know and love that actually has something that doesn't have this unit increment property? Well, there's the entropy function. Turns out that the entropy function is also a submodular function. The entropy function in this particular context is seen as a function of a set of random variables. So we have this large collection of random variables. So rather than being columns of a matrix, these are now random variables. And V indexes the set of all random variables, and a subset A corresponds to a subset of random variables. And f of A is the entropy of that set of random variables. So entropy is submodular. Why? Because conditioning reduces entropy. Exactly the diminishing returns property. If, on the other hand, if we have an entropy function where the random variables are either fully dependent on other random variables or fully independent, that's exactly analogous to the situation in matrix rank. But as we know, when we look at collections of random variables, that's almost never the case that random variables are either fully dependent or fully independent of other random variables. In fact, you can have partial independence, and conditioning reduces entropy. Conditioning doesn't set entropy to zero. So therefore, entropy seems like it would be a prime candidate to use for, say, the data subset selection problem. We just instantiate, we have V, which is our big data. We have a random variable associated with every data item. And then we just use this entropy function, and we find a set A that has the same entropy as the full set of random variables. We're done, right? No. The problem is that entropy is a beast of a function to estimate. Having done so myself back in my youth, when I was your age, it's so great to be able to say you're old, because now, I used to not be able to say that, but now I can say I'm old because I am old. But back when I was your age, I used to try to estimate entropy functions, and it was really difficult, and you come up with various different strategies, and you do various corrections and all sorts of things, and you'd spend weeks just trying to do one entropy query. So this gets back to Sanjeev's question: is what happens if a query is difficult? Well, entropy, just to compute an entropy query, you need to do an exponential probabilistic inference problem, and you need to do an exponential size density estimation problem. So entropy is not a practical function to use. Okay, it turns out that submodularity, however, has the benefit of, first of all, entropy is a submodular function. Secondly, entropy does not span all possible submodular functions. Submodular functions are a larger space of functions than the entropy functions. And thirdly, polymatroid functions sort of, in some sense, give you everything that you need to sort of instantiate an information function. And all submodular functions, in one way or another, sort of express the notion of abstract independence or generalized dependence, or sometimes what I like to call, and some people call, combinatorial geometry. And the idea is that, with this combinatorial geometry defined by a polymatroid function, there is a notion of independence, which is f of the union, which is independence really becomes additivity. So A and B are additive. That means independence. That in this abstract notion of independence, that's the definition of independence. There's the notion of conditional independence. If you know C, then A and B are independent. This is the notion of conditional independence in the abstract geometry space. This is how you measure it. There's a notion of dependence, or conditioning reduces valuations. So if we define, for example, f of A given B as f of the union minus f of B, and that being strictly less than f of A, basically means that B, in some sense, tells you something about A, except that it's in this polymatroidal sense of telling, not in this entropic sense of telling. It could be an entropic sense of telling, if it's an entropy function, but if it's not, it's something else.
A quick question.
Yep.
Could you just remind me what is the polymatroid definition?
So the definition of polymatroid is that it's submodular, monotone, non-decreasing, and normalized. And so that basically means it's non-negative. Because if it's normalized, it means that f of the empty set is equal to 0, and if it's monotone, non-decreasing, then basically it can never go negative, because as you add more stuff to the empty set, it can only increase, it can never decrease. Are there other questions?
So the monotonicity is needed only for the one which is the dependence part, because I'm thinking the first two don't seem to need it.
All of the above don't need it. None of them need it. So it turns out, this is something I wasn't going to talk about, that any submodular function, whether it's monotone or not, can be decomposed in terms of its sort of polymatroidal part and its additive part. And the additive part, you can think of, there's lots of different ways of talking about the additive part. You can think that if you're into sort of probabilistic models, you can think of them as unaries. You can think of them as the additive part. You can think of them as the independent part. Of course, something like entropy is already monotone, so therefore that's not done. But you can think of them as costs associated with individual items. It's a little bit. By the way, this decomposition is easily done. Right? You just sort of you subtract off from each item the sort of smallest gain, and suddenly it becomes positive and normalized and everything. And then because all these things are always true, the additive part essentially is just right away true. So that all that stuff cancels out, and you're left only with the polymatroidal part. So it really doesn't matter whether there's a polymatroid function or any submodular function. And then there are other notions of sort of information amongst collections of sets. So this is one version. There's also a sort of an inclusion-exclusion variant of this, which you get. So all of the kinds of information measures you get with entropy are also true of polymatroidal functions. Now, it turns out that many functions turn out to be submodular, and this is something I've seen in a number of fields. Submodularity has been discovered repeatedly many times but unbeknownst to the discoverers in the natural language processing community, in the computer vision community, in the operations research community, in the statistical physics community. Sometimes it's called different things. Sometimes it's called in the machine learning community, it's called attractive potentials. It's called ferromagneticity. I can't really say that word. Ferromagnetic assumption of a Ising model is a submodular assumption. And this is sort of, it seems like it's a very natural and common property. It shares with convexity the naturalness and the applicability. Although, as I was saying to a few people I was talking about before the talk, that it's not really correct to consider them discrete variants of convex functions. But there are lots of different submodular functions. Social network influence was shown to be submodular about 10 years ago. Many different models of social network influence. Viral marketing models. Combinatorial auctions often use submodular functions. Social welfare functions. Submodularity is the natural model for social welfare, where you have to divvy up a set of items to a bunch of individual groups, and where each group's evaluation of that set of items is submodular. All of that stuff happens. Network externalities is a great example. That's an example of a supermodular function where you have complementarities, sort of the negations of submodular functions. I don't want to go into all of these because that would distract us from this talk. So let's get back to big data and submodular subset selection. So we answered then basically the problem of data subset selection under the sort of roof of submodular functions becomes one of two approaches. One, we can sort of design a submodular function by hand. And this then sort of becomes an exercise in feature engineering, which is very similar to the kinds of feature engineering that we do in most machine learning domains. We know something about the data, and we design a function which is submodular, which is appropriate. A more modern approach, maybe, or actually maybe it's not more modern. Both of these are modern. But another approach is to actually try, in some sense, to learn the submodular function based on data. And I'll talk a little bit about both of these. So first of all, let's talk about document summarization, extractive document summarization. So these results are about a year old. Some of you might have seen this before. Do you have a question?
So, I'm wondering what is the relationship with alternative approaches to summarization, such as the following. I could have a data matrix, and what you're really trying to do is to select a subset of columns that are informative. So, one approach that has been exploited to do that is to say, well, the counting norm is just the number of columns that I'm going to select. And the way to relax that is by having some sort of norm, like the 2,1 norm of the matrix, which is a convex surrogate for the counting norm. So, the results from the compressed sensing literature say that under conditions not only on the function but on the data, you actually can get exact and the same type of results are applicable to these things. Therefore, what I see is that you're just at the end of the day getting conditions on your function, but you have no condition on the data.
Well, I guess there are relationships to compressed sensing and compressed sampling with respect to convex relaxations of norms. It turns out, well, there's actually a lot of different things. First of all, with respect to the compressed sensing literature, these kinds of assumptions that usually need are restricted isometry type properties, which may or may not be actually true of the data. I think that the submodular assumption on the data, on functions measuring the data, is probably more, first of all, it's easier to understand. I think it's more natural than restricted isometry-based assumptions. Secondly, actually, one can construct structured norms based on the loss extension of a submodular function very easily. This is some recent work, and in fact, many extraordinarily interesting norms are related to this.
One is forgetting about submodularity, because both the rank and the L0 norms and all of those are submodular. So the kinds of energy functions that are used are submodular, and these are just relaxations.
Yeah, I was going to say that. Yeah. So the other, this is a long discussion. With convex relaxations, oftentimes when there are so many answers to this question, I don't even know where to begin. That's the trouble I'm having. So on the one hand, there are relations, and the other is the restricted isometry-based assumptions, which are often not true. Number two, I'm sort of interested myself in discrete algorithms. And we've actually done some work on convex relaxations of just combinatorial optimization problems. And in many of those cases, one can actually come up with a relaxed surrogate, which then, in order to go back to the original discrete solution, you need to round in some way. Similar to how the L1, in many cases, when you do an L1 relaxation of L0, you still need to do some rounding. And that's true for other norms as well. Like, for example, the nuclear norm is a convex relaxation of the rank function, of a rank matrix. But I should note that the rank is, that particular form of rank is very, very different than the way that we were using the rank function here, the submodular function. So we're actually using it in some sense as the rank of a set of column vectors. The rank norm is often used as sort of like ranks of submatrices that are like two different sets of rows and columns. And those are used for things like collaborative filtering and nuclear norm based and that's a great example. But also there are relationships there as well via the loss extension, which actually allow you to express other more interesting norms than just these sort of simple L1, 2 norms and other sort of norms via the loss extension. So you have this infinite family of norms that you can actually instantiate simply by just looking at and designing a submodular function, which I think is amazing. So there are a lot of connections there. But I think in order to, I'm already like 5 minutes, so there are still more answers to that question I could give. But let's push on. But I want to get to some of these results. So actually, believe it or not, I do have some speech recognition results here, and I want to get to it. Because there's one interesting point that I think maybe I should skip the document summarization. So does everybody raise your hand if you know what document summarization is? Okay, great. So I'm going to skip that. The basic idea is like, here's the model. When you're doing extractive document summarization, the value of a sentence to the summary it seems reasonable to assume that that value of that sentence diminishes when it's considered in the context of a larger summary. So our assumption is that submodularity is a good model for extractive document summarization. Now this turned out to be a reasonable assumption because when we looked at the history of document summarization starting from like the 1998 Goldstein MMR results, maximum marginal relevance, to essentially work that had still been being done in 2010, many of those methods ended up being submodular functions. Although the scientists who were actually designing those methods didn't know that. And so they were actually optimizing their objectives using integer linear programming, which means that it doesn't scale. Whereas it turns out that if they had known that their functions were submodular, they could run the greedy algorithm, they'd have a guarantee. So our approach was to approach the problem starting from the idea of submodular design. How do you design a good submodular function for this problem? And we were quite successful. Here's basically the objective function. So, this looks like something that you could easily express with an integer linear programming. It's a discrete problem, hard maximum objective subject to some other objective, and you've got some integer constraints. And then you relax it, and you do an LP relaxation, and you solve it there, and then you do some rounding, and maybe you've got guarantees from the rounding, maybe you don't. There are innumerable different rounding methods, randomized rounding, and rounding to the nearest integer, all sorts of things. And it's important in those cases to actually be able to show that you do have a guarantee. The nice thing about this purely discrete algorithms is that there's no rounding algorithm. There's no rounding step needed. So this, just as an example of like running the greedy algorithm, takes about 1 second, whereas an ILP takes 17 hours. So there's huge differences in performance on typical document summarization tasks. And so obviously if you were to scale up to big data, 1 second is a more attractive wall clock time than 17 hours. So I'm going to skip over this because I want to get to some of the newer stuff. But basically, so officially I'm now skipping details, so if you don't understand what I'm saying, that's okay. Feel comfortable with not understanding everything I'm saying. So we use a number of different submodular functions, a coverage function which is submodular. It's based on needing a graph and a similarity measure between individual sentences in a document. A diversity reward function, which sort of, rather than penalizes redundancy, rewards the diversity of the summary. And mixtures of diversity reward functions, and each diversity reward function is based on a clustering of the data, and possibly a different clustering of the data. We evaluated this on a standard document summarization benchmark suite, which is the DUC. Corpora, there's I guess 4 of them, DUC04 through DUC07. DUC04 is query independent summarization. DUC05 through DUC07 is query dependent, meaning that you put in a query and you want a summary to be somehow relevant to the query that you're putting in, and hence is more akin to web search. And Rouge, actually this is something that we discovered. The metric that people use to score a summary automatically ends up being a submodular function. And so this is how you, people are familiar with BLUE in machine translation. Rouge is sort of the blue of document summarization. And there's a newer method that people use in document summarization called Pyramid. That's also a submodular function. So basically everything was submodularity in document summarization world, except no one was saying it. No one knew about it. I'm going to get in trouble because this is being videotaped. Can you erase this? Anyway, so we basically, we just sort of instantiated a submodular function, and we started getting very, very good results. And these were our results. And at each year we were trying this, we had the best results reported. And so this is on a DUC04 corpus. This is the DUC05 results. These were the best results reported. This is an example. Bigger is better, if I didn't say that. DUC06.
Can I ask a quick question?
Yep.
Really quick question. So, if I want to caricature submodularity, basically speed up, correct? This is speed up.
No.
It's not.
It's a mathematical assumption that allows one to use algorithms that have theoretical performance guarantees with respect to the objective that you're optimizing.
Okay, I'm just curious why you're getting gains.
Why we're getting gains? Because I think by looking at the problem from the perspective of submodularity and understanding the range that submodular functions can span, what can submodular functions do, and treating it as a submodular optimization problem and a submodular design problem, and knowing what we want a submodular function to do, we can set a submodular function that, for this particular problem, document summarization just works very, very well. Because by looking at it from in a higher level, in a more abstract level, we can sort of span a larger set of possible objective functions, rather than saying, oh, here's a function I think kind of works well, which happens maybe to be submodular, but not, we sort of were able to consider a wider range of techniques in some sense, all of which would have been seen as maybe different historically, but because they were sort of under the same submodular umbrella, maybe it's seen as the same. So we got the best reported results on these corpora.
So is it fair to say that the reason you're getting gains is that you're training the submodular function?
No, this is without training. This is still without training. I'll talk about the training
So
results.
in fact, I would answer Miles, maybe tell me if it's the way of answering it, that you're getting better results because the ultimate problem is to choose a subset of sentences, which is a very hard problem. And you're able to select these functions, which are submodular, and optimizing them is good, and they capture what is good about a subset of sentences.
Yes, that's right.
And that's what you're doing.
That's right. I mean, the way to think of submodularity, it's a model. It's a model of the world. Just like convexity is a model of the world, or an Ising model is a model of the world, or a hidden Markov model is a model of the world. I mean, is the world always submodular? No. Is the world always convex? No. Is the world always a hidden Markov model? Is the world always a deep model? No. But what we are interested in as machine learning scientists are applicable models of the world that have attractive mathematical properties. The attractive mathematical properties of graphical models has traditionally been either their decomposability properties, meaning that they can decompose and you can actually run inference on them efficiently. And the trade-off there has been to make enough assumptions so that you can actually either exactly or approximately run inference on the graphical model and make not too few assumptions so that it doesn't become inapplicable to the world. And so submodularity is just it's another way of doing a model. It's another modeling framework. And so it's not like a method to speed up. It's not. I don't think that's really a correct way or a wise way, to be honest, to think about what we're doing here.
So let me see if I can channel what Miles was asking, because I had the same question. Given that you just said all the functions are submodular anyway, why are the other people playing in this competition optimizing the same submodular functions that you are, but doing it by ILP, so they got higher performance, only slower?
Well, it's for several reasons. One, at the time, it wasn't known that what they were doing was submodular. So in their papers, they did not realize that their objectives were submodular. Number two, they had one objective where by looking at the range of submodular functions, we were able to span lots of different ones. And number three, this gets back to the conformity result, so that with ILP, oftentimes, yes, you can get the exact solution if you spend exponential times, but oftentimes they would do early stopping, or if you're doing continuous relaxations and you do rounding, you're going to get some error anyway when you do ILP. And oftentimes if you do a sort of heuristic rounding, you don't have any guarantees. The conformity result says that depending on the curvature of the submodular function, the guarantee is much better than 1 minus 1b. And most of the functions we have are not so curved. And so our guarantees are probably much better. When we ran the ILP on our function to completion, it turned out that we were getting approximations on the order of 98-99%, much better than 0.63. So we were almost getting the optimal solution with the greedy ILP. And that has been since done in a number of other cases, and people have found that, again, partly based on consortium, and partly possibly based on and this is a lower bound result. Maybe, maybe for a particular instance, the bound on this particular instance for greedy is greater. But that can only be analyzed by looking at that particular instance of a function. So, but I'm giving you long answers. Last year we actually learned these functions in a max margin framework, and this gets into a lot of detail. But there was a method we called submodular shells, which is a nice name, and if you want to understand what a submodular shell is, then I suggest reading the paper. But the point of it is the results, so that we improved on our 2011 results in the 2012 results with submodular shell. So this is DECO 4 result, and at the time this was the best result ever reported, improving on our previous result. I should mention that determinantal point processes were also applied on this, and they got slightly better results, but they didn't just use determinantal point processes. They also used minimum Bayes risk decoding with samples of size 5,000 to 1,000, so they were extraordinarily computationally complex. Our results were just a very simple Boole algorithm, which runs in basically linear time. So it's a very, very fast and very, very scalable inference algorithm. But we also tried this on DECO 5, which was the query specific, and we got these. I think this is still the best results ever reported on DECO 5. The same with DECO 6 and DECO 7. And I want to push forward because I want to talk about these speech results, because we recently have been looking at speech data subset selection. And the basic idea here is, I think some of you guys here, from what I've been talking, I talked to some of you, and some of you I think this would be quite useful for. But you have 1,300 or 2,000 or maybe 50,000 hours of speech to train a speech recognition system on. And because of, in some sense, the lack of coordination that has occurred in collecting the speech, which is rightfully so, and this is correct to not necessarily have to coordinate, there's an enormous amount potentially of redundancy in the training data. And when there's a redundancy in training data, you're spending compute cycles training your model, which is particularly an acute problem when you're training repeat models. You're spending compute cycles wastefully. And so therefore, rather than taking 2 days to train a model, you're taking 2 weeks or maybe 2 months. And in those 2 months of time you're spending one model, maybe if you had a good subset of the training data, you could try lots and lots of different variations of the model. And then, in the end, come up with a much, much better configuration of the model that you're ultimately after. So that's the goal. So we want to choose a subset that is representative. And we don't necessarily say that a subset's going to be as good, but what in this particular work I'm about to tell you, we were interested in drastic reductions in the size. Like if we were forced to have maybe a 1 to 2 order magnitude reduction in the training data set size, how good can we do? I should mention this is distinct from the other problem, which is finding the smallest subset that retains the performance of 100% of the data. That's a different problem which we didn't concentrate on. So this is the problem. This is the first problem. This is, with drastic reductions in size, how good could we do? And it's motivated by this kind of plot, which I've shown you already before. So what we could do, and this gets back to instantiation, we could instantiate some of these functions. And some of these functions basically, some of these submodular functions require a graph. Like the facility location function basically says that you need to have a weighted graph, and where the edge weights correspond to some notion of similarity between speech utterances. And so this actually brings to bear the long historical work in the speech community on similarity measures between utterances, which might be very, very different, and might have different lengths, and so on and so forth. And in past work, we've actually done this using things like the Fisher kernel. This guy also requires a similarity measure. But what we did in this work, which is sort of more similar to, I think, some of the work that people have done in feature induction methods in natural language processing, is instantiate what we're sort of calling feature-based submodular functions. So the idea is as follows. Any given speech utterance can be represented as a vector of features. And a vector of features, the elements of that feature vector might correspond to something like the count of that feature, or it might be, say, like a TF-IDF normalized version of that feature, or it might have some other modifications. But whatever, the point is that you've got some object. It's a structured object. The speech utterance is a structured object. It's variable length, and there's dynamic time warping that's going on between different speech utterances. And you have a fixed length feature vector. And then we instantiate a submodular function in this fashion by saying, let's say U is the set of feature vectors. Let's zoom in a little bit on this. Script U is a set of feature vectors, and we essentially sum over all features, and we apply G, which is a concave function, to some score associated with the feature item, lowercase u, and the set of things that we're interested in. And the set of things we're interested in is basically measured by this modular function. So basically, this is just summing over this should be S in S. Sorry, this is the typo. I can do real-time typo fixes here. So there you go. So S in S of MU of S. So it's a modular function. So basically, every single feature is represented by modular functions, but it's turned into a submodular function thanks to this particular concave function G. Okay. Okay. Now, why is this a good function? Because on one hand, it sort of leverages all of the work that people in both the speech and the natural language, and many machine learning communities, the vision community as well, have done on coming up with good feature representations for objects, whether it's SIFT and GIST in computer vision, or whether it's like the features that go into a log linear model in natural language processing, or whether it's Gaussian mixture component ideas in speech recognition. They're all in some sense features. So there are a lot of details I'm skipping out because of time, but we applied this to 1,300 hours of a combination of Fisher, switchboard, and all of the other nice large data sets that are available in the speech community. And again, like I said, we wanted to look at data set sizes that were drastic reductions relative to the full data set. So we were concentrating on 1% to 20%. So 1% is 2 orders of magnitude, 10% is 1 order of magnitude. And this gives some details of the test set. So basically what we're doing is we're taking the training set, taking a subset, training a brand new system on only that subset, and then testing it on the, maybe tuning it a little bit with the dev set, and then testing it on the test set. And then we take another subset from scratch, train it, tune it a little bit on the dev set, test it on the test set. And we just repeatedly take a different subset. And each subset, each speech recognition system is completely formed independently for each subset. And each speech recognition system, moreover, is optimized to be as good as possible on the dev set. And then there are 2 baselines that we wanted to compare against. One was just random sampling, where you just take a random subset. And another is a method, this is not their name for it, but we're calling it the histogram entropy method, which is method, actually I forgot the year here, this is from 2007, from TMU. So we have, the first results are for Gaussian mixture-based speech recognition system. I should mention this is SRI's speech recognition system that they use. It's a large vocabulary state-of-the-art speech recognition system. I don't know if it's as good as Kaldi. I think that Kaldi is sort of, I take it back. They use Kaldi for the deep system, so this is as good as Kaldi because it is focusing Kaldi. But these are the results for the random case. HE is, there are 2 different variants of the histogram entropy. One is whether you use histogram entropy. Actually, I didn't say what histogram entropy is, but histogram entropy is a non-submodular method whereby what you do is you essentially look at a subset and you look at the histogram of the features of that subset, and then you compute the entropy on that. That's very different than the entropy of a set of random variables. That's an entropic function. It's the entropy of the histogram formed by the set of features, but it's not submodular. It's not even monotone. Because what can happen is you can actually saturate like a uniform distribution, but then if you add something else, it goes down. It's not even monotone. It's not submodular. And they have a greedy-like algorithm that they use. And we use a submodular method, and we get significantly better results. So this is all of the data, all 100% of the data. Now, in a deep system, all of the results are better. But the results, I think, in the case of the submodular subset selection are even better. And I thought that it would be good to sort of look at the results together. So with respect to, I thought that looking at this result and this result, so this is the deep system down here, and this is the Gaussian mixture system up here. What's interesting is that with the deep model at 5% of the data, we can do as well as the Gaussian mixture system does with 100% of the data. If you use the submodular selection method. If we use either the random selection method or the histogram entry method, the deep system is not as good as 100% of the data in the Gaussian mixture system. So from the perspective of developing and having a quick turnaround time of a deep model speech recognition-based system, you can actually get a respectable, with the right subset for the training data set, you can get a respectable word error rate and possibly try some different variants much more rapidly with a factor 20 reduction in the amount of training data. And this is, I think, quite significant. Yeah.
So I would argue that the more interesting case would be if your feature functions weren't dependent on transcription, so that you can use these submodular functions in the context of adaptive or active learning.
Let me give me a chance to. I've got another slide on that. So that's a very good point. First of all, so thank you for the question. And indeed, I don't think I even mentioned that these results were based on an alignment, a forced alignment. So these were based on the word alignment of the Fisher corpus. And indeed, absolutely, what we don't want to do is have to transcribe, even at the word level, which is pretty painful, but we don't want to have to do that. So we've done that recently in the case of the TIMIT corpus. So this is strictly, completely unsupervised. We haven't yet done this in the case of Fisher and the speech systems. But in the case of TIMIT, it turns out that this approach also works with an unsupervised approach. Now, the method of unsupervised supervision was actually fairly simple, and actually it was somewhat akin to the work on speaker ID that people have done in the past. And that basically is where you just train a Gaussian mixture system on all of the frames of all of the speech. So basically it means that you could permute the speech utterances in terms of frames and you get the same thing. But somehow those become the features of the speech utterance. And this shows at different percentages the different results. So I should mention that like this guy here is the random result. These guys are submodular. And this is the min. And this is the max. And it's the min and the max over 100 random samples. So like this is the best you can hope to do over 100. I'm running out of time. So, okay. Anyway, the point is that it seems to work also in the unsupervised case. We're hopefully trying to get funding to do this in the unsupervised case for sure as well. But, anyone wants to collaborate on this or work on do experiments? That'd be great. So last set of results are on machine translation. I just want to mention that briefly that something similar seems to have happened in statistical machine translation with regard to data subset selection that happened in data set summarization, which is that a lot of the methods that we looked at end up being submodular methods, including the unseen n-gram function of Eck in 2005, the cross entropy. That actually ends up being a modular approach, so it's actually a very simple modular approach. And the feature decay method of Gatipi, those are all submodular functions. And so we approached this problem with a submodular function. Here's our submodular function, which I'm not going to get into the details of. But with this submodular function, you can actually get better machine translation results. So this column is the submodular results here. This is the previous sort of state-of-the-art, the cross-entropy method. And we're getting better results on a number of different machine translation corpora, Transcac task, Europarl task, and also this English task. For this. And these are blue scores, by the way, so bigger is better. So in any event, I have to finish now, because otherwise you're going to run out of videotape. And we're also working on some image summarization. But the whole point is that when you have a big data set, rather than repeatedly processing that big data, one option to essentially deal with redundancy is to somehow do summarization. And it seems like submodular functions and the abstract independent space that they instantiate is a useful way. I think it's fair to say it's useful, it's practical, and something that we should, in the machine learning community, consider when we actually are faced with machine learning on big data sets. Here are some references. I also want to just give a brief plug to a tutorial on submodularity that I'm giving at NIPS. To be honest, just touched the surface of the technical details of submodular functions. There's a lot of mathematical richness and actually real beauty in submodular functions, which if you want to get a little bit of a taste of, you can come to NIPS, then come to the tutorial. And furthermore, maybe someday we'll be ready for this book. So thank you very much.
We need to be out in about 5 minutes, but I think that if somebody has a really burning question, please do ask it. Never mind, then we have 5 more minutes.
Yep.
So a lot of times people do system combination. Does it make any sense after you, let's say you've boiled down, you've done your thing, you've got a bunch of samples of very small sizes, or maybe they'd all be the same. I don't know. Can you get small samples of your data set and then combine those systems in any way afterward, in any sensible way if you selected those samples with the methods you've described?
Yeah, there are ways. I mean, there is something to be said to the utility of combining things that aren't identical. Because if things being combined are identical, then you get the identical results. And in order to ensure that things aren't identical but still in some sense representative, you want diverse sets of subsets. And submodular functions, of which I didn't mention, but determinantal point process is a special case of a submodular function. That actually, those sorts of ways are strategies for that kind of thing. Although there isn't as of yet any result that I know of where people have, for example, come up with improved, say, variance reduction results in terms of, say, diverse samples as opposed to random samples. But that doesn't seem to be out of reach. I would be surprised if that was out of reach.
Okay, I think that we may. Thank you very much.